last section we're going to look at this week is 6.5, and it's on solving triangles. Does anyone have an idea what does that mean? Like to solve a triangle? What do you think it means to find?
Find all the angles.
Find all the angles, yep. And all the sides, yep. So the kind of triangles that we're going to be solving are right triangles. Later on, we're going to do triangles that are not right triangles. But what does it mean if you have a right triangle? Yeah.
One of them is always 90 degrees on the angles.
Yeah. So we're going to talk a little bit about the kind of triangles we're going to work with, and then we'll get into how we solve them later in 6.5. So we're going to be solving triangles that have a 90-degree angle. What's the name of the side that's across from the 90? The hypotenuse. And what do we call the other two sides?
Opposite and adjacent.
We are going to use those words, yes. I'm thinking of another word. The legs, yeah. Yep. Okay, here's pretty much a diagram of what we just said. Actually, one more thing. What do we use to label the sides if we don't know them? You can use X. We normally use A, B, and C because there's a theorem that can help us find a side if we don't know it, as long as you know the other two. And does anybody know what that theorem is? Yeah, what is it? The Pythagorean theorem. Yep. So this is a way to represent the formula, but the idea of the formula is if you square one leg, and then you square the other leg, and you add them together, it equals the hypotenuse squared. Whether you call the sides ABC, XYZ, that doesn't really matter. But ABC is the most common. Okay. Remember, this is a Greek letter, and a lot of times we don't know an angle in trig. We always use a Greek letter to basically name it temporarily. What is that Greek letter? Theta. Yep. And it has to be between 0 and 90 degrees. Why does this angle have to be between 0 and 90? I mean, you can have a triangle with an angle bigger than 90, but not in this kind of problem. Yeah.
Because all of the angles added together are all going to be equivalent to 180 degrees.
So all the angles add up to 180. Okay.
And one of them is already 90, so you have 90 left for two angles.
Right,
And
that's the key.
You can have a zero angle.
Yep. And you've already used 90 for the right angle, so the other two added together have to add up to 90. Yeah. Okay, so any questions on the terms hypotenuse, legs, or what the Pythagorean theorem is? Okay. So we're going to look at the 6 trig functions again. So the sine, the cosine, the tangent. You tell me, what are the other 3?
Cosine, cosecant.
Cosecant?
Yeah, cosecant, secant, and cotangent.
Cosecant, secant, and cotangent. Yeah. So we've already looked at them before. And when we did them in section, I think it was 6.2, we did them on a unit circle. So we had a coordinate. Sine was y, cosine was x, tangent was y over x. We're going to look at the same trig functions again, but we're not going to do it on a circle. We're going to do it on a triangle now. It's the same thing. It's just like a different way of looking at it. When you define trig functions using a right triangle, all the trig functions are a fraction of 2 different sides. And there's 6 different ways you can pair up the sides we're going to use. The sine is when you take the opposite side and divide by the length of the hypotenuse. So these represent lengths. Length of the adjacent, over length of the hypotenuse. And tangent is length of the opposite over length of the adjacent. If you're not sure what opposite and adjacent are, I'm going to show you what those are in a second. Now, think about what happens if you divide two lengths. If you take 6 feet and you divide by 7 feet, what happens when you divide those? Yeah?
Do the feet cancel out?
The feet cancel out. And all you're left with is a pure number that has no label. That's how trig functions work. When you take the length of the adjacent and divide by the length of the hypotenuse, you get a number that does not have a label. It's just a number. It's not degrees, it's not radians, it's not feet, it's just a number. Okay. All right, now let's look at the three on the right. So the cosecant, secant, and the cotangent. The way I pair them up, there's a connection between the one on the left and the one on the right. Does anybody remember what the connection is? Like what you do to the one on the left to turn it into the one on the right? Yep. It's the reciprocal. So what do you think the cosecant would be?
Hypotenuse over opposite.
Hypotenuse over opposite. Yep. And the secant?
Hypotenuse over adjacent.
Hypotenuse over adjacent. And the cotangent?
Adjacent over opposite.
Adjacent over opposite. Yep. And there's a trick that some people use to remember the three on the left. Does anybody know what trick I'm thinking of?
SOHCAHTOA.
Yep, the SOHCAHTOA. So sine is the opposite over hypotenuse. So S-O-H. Cosine is adjacent over hypotenuse. C-A-H. And tangent is opposite over adjacent. T-O-A. That's just a trick some people use to try to remember it. When I asked one year if anybody knew the trick to remember it, you guys got it right, SOHCAHTOA, that's it. But one year when I asked, people said Sacagawea. Yeah, not quite. Sacagawea is not going to help you with tricks. I'm sorry. But SOHCAHTOA, that'll help. Right, so really, you just got to remember the three on the left, and then you just flip them to get the three on the right. Now, the hypotenuse. Where is the hypotenuse? It's always across from a 90. That never changes. Okay? Something like similar in this room would be like up. It doesn't matter if I face in your way, or you're facing my way, or you face the door. Up is the same way for everybody, no matter which way you face. But opposite and adjacent, those are what we call relative terms. Relative, or it's kind of like left and right. Those directions are relative to which way you are facing. So for me, left is the door, right's the window. For you, it's the opposite because you're facing a different way. So the way you determine which way you're facing in a triangle is they mark the spot that's where everything is being labeled from. It's like this is your perspective. You're here. Opposite is the side that's furthest away. You're standing at that angle and you're looking out. It's the side that isn't connected to the sides that are next to you. Okay? It's furthest away. Adjacent is the side that's right next to you. And you might say, well, there's two sides next to you. Well, the top one already has it. That's the hypotenuse. Okay, so they'll always mark kind of the perspective in the triangle. How about if I did this? What would not change?
Hypotenuse.
Hypotenuse wouldn't change. So that's still the hypotenuse. But where's the opposite now? Yeah, the opposite is the side furthest away, and the adjacent is next to each. Bless you. Okay, so any question on what I mean by that, relative terms? Okay. So when we're doing right triangle trig, and let's say I ask you to find the sine of 45 degrees. Some people might draw a 45-degree angle like that. Some people might draw it like that. If I find the sine of 45 in this triangle, or I find the sine of 45 in this triangle, do you think there will be a difference between the two answers? No, there shouldn't.
That's supposed to be degrees, right?
Yeah, that's degrees. And that's because if you draw two triangles that are similar, similar means one triangle could just be larger or smaller than the other. The trig functions always have the same value. Doesn't matter if you draw a really big 45, 45, 90 or a really small one. Trig functions always have the same value for a given angle. So let's look at two 30, 60, 90s. Okay, these are two 30, 60, 90s, and they are labeled properly. Both of them have correct sides. And let's start with the one on the left. And let's find the cosine of 60. "60 is your perspective. So pretend like you are standing right there. You're not standing at the 30. What did we just have for a definition for cosine?
Adjacent divided by hypotenuse.
Adjacent divided by hypotenuse. What side is adjacent to 60 in the small triangle? 1. And what's the hypotenuse? 2. So in the small triangle, the cosine of 60 is 1/2. Now let's find the cosine of 60 in the bigger one. This is a triangle that's a scale factor of 2. It's twice as big as the one on the left. Okay, so again, here's your perspective. What side is adjacent to the 60 in the big triangle? 2. And cosine is adjacent over hypotenuse. What's the hypotenuse? 4. And what does that reduce to? 1/2. Okay, so the point is, it doesn't matter how big or small your triangle is. The cosine of 60 is always going to be 1/2, no matter what kind of triangle you draw. Size-wise. So that's what I'm getting at with this. So we call these two triangles similar. They're not congruent. Congruent means they'd be the exact same size. Similar just means they have all the same angles, but it could be a larger or smaller version. Okay. Question on that idea? Okay. All right. Don't write this yet, because I want you to write something before it. But what I'm going to do is I'm going to give you a trig function, and I want you to use it to find all the other ones you don't know. So there's 6. I'm giving you 1. So you need to find the other 5. If I tell you that the sine is 5/6, what have I really told you? I've told you 2 things in the triangle. Yeah?
The opposite length of the hypotenuse length.
Yeah.
The opposite length is 5. Hypotenuse length is 6.
I told you the opposite length is 5 and the hypotenuse length is 6. So I've given you 2 out of 3 of the sides. How do you get the third side if I give you 2 of them? Yeah?
Right here.
Exactly. Okay, so let's just write that down. So to find all 6 trig functions, if I give you one of them, first use that trig function to label 2 of the sides in the triangle. Could be the opposite and the hypotenuse. Could be the adjacent and the hypotenuse. Could be the opposite and the adjacent. It'll have to be one of those 3. Once you know 2 of the sides, use the Pythagorean theorem to find the 3rd side. And now, once you know all 3 sides, you can determine any trig function that you want. Yeah.
How do you get, if you're given one?
Well, you're given one trig function,
Yeah.
so you're given a fraction.
And then you can find the inverse of it? Is that what you're saying? Like, how do you find the second one?
Well, we're going to go through an example. Yeah, we're going to do the one that I just had on the board. So they're going to give you 2 sides. You're going to label the triangle, and then you're going to do the Pythagorean theorem with those 2 sides. That'll give you the 3rd side, and then you can figure out any trig function. Alright, let me keep that up. Let's try it. Okay, so it says, let theta be an angle. We don't know what the angle is. Could be 20 degrees, 30 degrees, we don't know. But we know that the sine of it is 5/6. Okay, so let's draw it. Okay, so you have to draw a right triangle, and you have to put theta somewhere in this triangle. It can't be the 90. It can never be the 90. It has to be one of the smaller angles. Let's put it here. If you put it up here, you're going to get the same answer. It's just like your triangle is going to be turned. It's the same thing. The sine is 5/6. What's the definition for sine again?
Opposite.
It's opposite divided by hypotenuse. So the top side, that's the opposite. So that's 5. And the bottom side, that's the hypotenuse. So that's 6. We don't know the bottom side. That's what we have to figure out. What could we call the bottom side for now?
RC. Adjacent.
So it's the adjacent side, and if we're going to use a theorem, we need a letter for it.
B.
Yeah, we can call it. You probably use A or B. Don't use C, because C is generally reserved for the hypotenuse. Okay, but you could use A or B. Which one did you say, A or B?
I said B.
B. Okay, so we use B. And now let's solve for the bottom side. So we're going to have 5 squared. Actually, let me do it up here. 5 squared plus b squared equals 6 squared. So I filled in these 3 things into the Pythagorean theorem. Okay, what's 5 squared?
25.
So 25. And b squared, we don't know. What's 6 squared? 36. So we're going to have to bring the 25 to the other side. So what's b squared?
Equals 11.
Is 11. So then what is b?
11 squared. I mean 11 square root.
Yeah. When you're doing a problem that asks you to find all the trig functions, don't round that off. Just leave it as the square root of 11. Okay, now we know all the sides. Okay, I'm out of space, but hopefully you have a little more space. I'm just going to jump over here and write down these 3 things. now, technically the first one, we already have that. The sine is 5 over 6. So then, what's the cosecant?
6 over 5.
Yeah, that one's easy because we were given the sine. So all we have to do is flip it. Okay, let's do the cosine. What's adjacent over hypotenuse going to be?
Square root of 11 over 6.
Square root of 11 over 6. And is that an okay final answer? Square root of 11 over 6? Yeah, that's fine. No problem with that. Okay. How about tangent? What's
5 over square root of 11.
It's going to be 5 over the square root of 11. Is that an okay answer?
No.
No. We don't want to leave that square root in the bottom. So what do we multiply by to fix it?
Square root of 11 over square root of 11.
11 over square root of 11. That gives you what in the bottom? 11. And in the top?
5 square roots of 11.
5 square roots of 11. Okay. Now, let's do the cotangent. We know we have to flip the tangent. Well, you can either flip what we had originally, or you can flip the final answer. They're the same thing. That's why it's equal to it. Which one would be better to flip?
The first one.
Yeah, why?
Because you have to reflip it. So, because the square would go to the bottom if you flip the final answer.
Yeah, if you take the final answer and you flip it, the square root goes back to the bottom. You have to fix it all over again. If you take what we had originally and flip it, square root goes to the top and you're done. So square root 11 over 5. And how about my secant? Anyone think they can tell me what that one's going to be? All fixed. Final answer, no square root at the bottom.
6 times 11 over 11.
Yep, 6 square root of 11 over 11. And those are the 5 trig functions they wanted you to find. Okay, any questions now? Let's try this one. So find all 6 trig functions. Okay, what's the first thing I have to do before I can start finding all 6? Yeah, I gotta find the hypotenuse. Yep. And since we don't know the hypotenuse, Sean, what's the label we normally use for the hypotenuse?
Not sure.
Would help. I mean, you can technically use any label you want, but just so we don't confuse it with other things, we should stick with this letter. Excellent?
See?
Yeah, let's just stick with using C. And Jack, can you set up the Pythagorean theorem for me using the 5, 12, and the C?
Yeah, so 5 squared 25, which is 25 plus 12 squared equals c squared.
Okay, and you said 5 squared, that was 25,
Yeah, plus 144.
plus 144. So that's 169 for C squared. And what does that make C? Yeah,
13.
13. So we get a nice answer.
They're not superstitious.
When you get all 3 sides that don't come out to any decimals or fractions, that's called a Pythagorean triple. 5, 12, 13 is one. 3, 4, 5, that's another one. There's millions of them. Okay, but that's a common one. 5, 12, 13. All right. And now let's do our trig functions. It did say to find all 6. Now remember, everything is from the perspective of theta, which is in the lower right. So opposite is 5, adjacent is 12. TJ, what do you think my sine would be?
It would be 5 over 13, or is it C13?
No, the C is what we solved for, so we don't need that label anymore. It's just because we didn't know it, but now we do. So we're
5 over 13.
5 over 13. Yep, so 5 over 13. Brady, how about my cosine?
12 over 13?
12 over 13.
Does it say J or is that 5?
That's a 5.
Okay.
My tangent. How about, yeah, Jake?
5 over 12.
5 over 12, yep. Okay, Zach, on cosecant?
12 over 5. 13 over 5.
13 over 5, yeah. Okay, so 13 over 5. Okay, my secant, how about Jacob?
13 over 12.
13 over 12. And David, what about my cotangent? All right, so what we have to flip something to get the cotangent. Which trig function do we flip? Yep. Flip the tangent to get the cotangent.
12 over 5.
12 over 5. Okay. Now keep in mind, we did not find the angle there. We don't know that this angle is 42.7 degrees or whatever it is. That wasn't the goal. That's going to be the goal tomorrow. Any questions on that? All right, so this one says, use the diagram below to find the 6 trig functions of 45 degrees. Now, technically, they could just give you a diagram like that. They don't have to label anything for sides. What did we say earlier about the size of the triangle in terms of finding the trig function?
It doesn't really matter.
Yeah, the size it doesn't make a difference. It doesn't matter if you use a big 45, 45, 90, if you use a small one, you can use any size 45, 45 you want. So the easiest 45, 45 to work with would be ones that don't have really big numbers. So I would let this side be 1. And if the bottom side is 1, this is isosceles, because it has 2 angles that are the same. What does that mean the height would be? Yeah, the height would also have to be 1. Because in an isosceles triangle, the 2 sides are equal. And then the hypotenuse, we could find using the Pythagorean theorem. What would the hypotenuse be in this case? What would it be?
Oh, yeah.
We can't have all the sides be 1, because then it would be equilateral. Yeah?
It would be the square root of 2.
It would be the square root of 2. Yep. Now again, that's not the only 45, 45, 90 you could use. If you want to do a bigger version of it or a smaller one, you could. I just like having 2 sides that are 1s. Now, it says 45 degrees. So which angle should be our perspective? Either one. It doesn't matter because if you pick this one in the bottom, opposite is 1. If you pick this one at the top, opposite is still 1. Doesn't matter. It's going to come out the same. So let's pretend like we're standing right there. So the only difference in this problem is we actually know the size of the angle we're working with. In the last problem, we had to use a letter. We didn't know what it was. Doesn't change how we do anything though. Alright, so let's start with the sine. How about There. What's going to be the sine of 45 degrees?
So 1 over square root of 2.
Perfect. It's going to be 1 over the square root of 2. And can someone tell me what you get when you fix that? Yeah.
Square root of 2 over 2.
Yep, perfect. Square root of 2 over 2. Okay, so there's the sine. How about the cosine of 45? Yeah. It's going to be the same thing because opposite and adjacent are the same. So that's also square root of 2 over 2. And what about the tangent? What's opposite over adjacent?
It's 1.
It's going to be 1. Simple. Okay. And what would you do to those 3 to find the next 3? Flip them. So I'm just going to find the 3 trig functions. And you could flip them if you wanted to know the other 3. Any question on how you would flip them? It's no different than the other ones we flipped. Alright, so there's that one. Let's try this one. Let's find the 3 trig functions. Okay, when I say 3, I just mean sine, cosine, and tangent. Just those 3. All right, I need a triangle. So I'm going to use that triangle, and I need to give you a question. Find the 3 trig functions of, you want to do 30 or 60? Doesn't really matter. 30. Okay. That's an equilateral triangle. So in order to find the 6 trig functions of 30, I need a diagram that has a 30 in it. Well, what are all the angles in an equilateral?
60.
Yeah, so we've got a 60. There's no 30 in there. But does anybody see something I could do to that triangle, and it would make 2 triangles, and I would have a 30, a 60, and a 90? Yeah?
Split in half.
Yeah, if you draw a line right down the middle, it's not exactly down the middle, but let's fix it. Close enough. Okay. Now, let's look at just this triangle right here. I'm going to pull that off to the side, and we're going to label it. Okay. What's the angle in the lower left? Yeah, that's a 60. And in the lower right?
90.
That's a 90. And they all have to add up to 180. So that's 150. So what about the one at the top?
30.
30. So when we do the problem, that's going to be my perspective. The only thing I need is some sides. Okay. Does it matter how big or small I make? No. So I'm going to give you a hint. How does this side compare to that side? It's half. So what's a nice number that we could label this as from here to here, that we could take half of it and not have to worry about a fraction? 2. So let's make that side 2. This is equilateral. So what does that mean?
All sides are 2.
All sides are 2. You don't have to pick 2. You could let all sides be 1, 3, 5, any number you want, but they all have to be the same. Now let's go back to the red triangle. Because of the numbers we picked, we can label that one now. What's the hypotenuse in this red triangle? 2. That's 2. That's that side right here. How about the bottom side? 1. That's the one where if you pick an even number when you label it, it just gives you a nice answer right here. So that's 1. The problem is this side. How are we going to get that? Pythagorean theorem. Yep. Let's call that side A. So we have 1 squared plus a squared equals 2 squared. Okay. What's 1 squared? 1. And 2 squared? 4. So a squared is going to equal 3. So then what's a? There you go. There's nothing you can do to get a nice answer there. It has to be square root of 3. But that's one way to pick your own labels and make the triangle that you need to solve the problem. Okay. Now, I want the sine, the cosine, and the tangents. Okay. What's the sine of 30 degrees?
1/2.
Yep, 1/2. Oops, I forgot 30 degrees. What's the cosine of 30 degrees? Square root of 3/2. And the tangent of 30 degrees. Remember to fix it if you need to fix it so the root's not in the bottom. It's going to end up being square root 3/3. So any question how we're fixing those roots? This comes up a lot in trade. Just quickly fixing the root so it's not in the bottom. All right, and that's how you do it. And when I said to you guys, do you want to do 30 or 60? It wouldn't have mattered which one you picked because the triangle I was going to make had the 30 and had the 60 in it. The only difference is if you use the 60, the opposite and adjacent perspective switches. That's all. Okay. Is there any question on that one? That's what we just did. Okay, last thing. Well, I kind of already showed you, but if two angles are complementary, it means they add up to what? It means they add up to 90. Now, we answered this question earlier. When you draw a right triangle, why do angles 1 and 2 have to be complementary? Yep.
Because there's 180 degrees in a triangle, and if 90 degrees is already being taken up, the other two have to equal 90.
Yeah, exactly. Okay, they all have to add up to 180, and you've already used up 90, so the other two have to total 90. Well, if they total 90, that's complementary. Yep. That's the diagram that we use when we don't know any of the sides of the angles in a right triangle. We use the ABC for the sides, and we use Greek letters for the angles. Does anyone remember what's the name of this Greek letter? It's the one that's across from A. Alpha, yep, so that's alpha. And how about the Greek letter up here across from B? Beta. Yep, alpha, beta. And the reason I do it that way, and a lot of other books do it that way, is because then there's no confusion. If I ask you for a Greek letter, you know you're finding an angle. If I ask you for an English letter, you're finding a side. If you get into using these capital letters for angles and lowercase letters for sides, then it gets confusing. Because, first of all, depending on the letter you pick, the capital and the lowercase letter might look the same. So that's a problem that things can start getting confusing. And if I ask you, let's say I write find C. Well, is it find capital C or find lowercase c? You can't tell which one I mean. So when I use Greek letters, those are angles. And when I use English letters, those are sides. All right, let's take that diagram and let's find something. It's not going to be numeric. There aren't going to be any numbers. I just want to know what the sine of alpha would be. Opposite over hypotenuse, yes. It would be A over C. Now, let me show you something. If you put the word co in front of that function, what do you get? Cosine. Right? So if you put the word co in front of it, you get cosine. Right? So let's do that. And what angle in this triangle is complementary? Or in other words, what angle do you add to alpha and it gives you 90?
Beta.
Beta. Beta is complementary to alpha. So I put the word co in front of that, and I put an angle here that was complementary. Let's see what this comes out to. Adjacent over hypotenuse. If you're at beta, adjacent is A, and hypotenuse is C. Came out exactly the same. All right, let's do one more. Let's do tangent of alpha. Okay. What's the tangent of alpha in this case?
A over A. No, A over B.
Tangent is going to be opposite over adjacent. Okay. Now I'm going to use a different trig function. If you put the word co in front of tangent, what trig function do you get? Cotangent. That's called the co-function. You put the word co in front. Cotangent. And we already answered this, but what angle is complementary to alpha? Beta. So from here, what is the adjacent over the opposite? Adjacent over opposite is A over B again. Okay, so I said something earlier, I don't know if I wrote this down ever, but cofunctions gives 3 pairs. What do you think the cofunction is for sine?
Cosine.
Yeah, put the word co in front of it, cosine. That's one pair. Another pair is secant. And what do you think the cofunction is with secant? Co-secant. And there's one more pair, tangent. And what do you think the cofunction is that goes with tangent? Cotangent. So those are the 3 cofunctions. And that leads us to what we just found. If you take co-functions, like tangent and cotangent, and you take complementary angles, like alpha and beta, they will always come out the same. A over B, A over B. So cofunctions of complementary angles always come out the same. So yeah, it's a very, very, very specific situation. But if you have it, then you know they are the same. Here's an example with numbers. Now I don't want to find the sine of 10. I just want to find something that's the same as it. What's the cofunction for sine? Cosine. And what angle is complementary to 10? 80. Okay, let's just check. Put the calculator in degrees. If you take the sine of 10 and you take the cosine of 80, they come out exactly the same. So cofunctions of complementary angles always come out to the same number. So, how could you use that to simplify that? I have the sine of 35 minus the cosine of 55. First of all, that and that are what? Those are cofunctions. 35 and 55 are what kind of angle?
Complementary.
So we have cofunctions of complementary angles. So what do we know about that and that? They're equal. What's in the first red box and the second red box are exactly the same number. We don't know what the number is, but we know it's the same. That's all we need to know. So what would this come out to?
0.
Yeah. The answer would be 0. Because we're subtracting two things that are the same. Now that wouldn't work for addition. Because if you add two things that are the same, you don't always get the same thing. You get whatever you started with doubled. So whatever that would be. But if you subtract two things that are the same, you always get 0. And how about this one? Yeah, why is it going to come out to 1?
Because they're, what is it, co-function?
These are cofunctions, yep.
They're co-functions and the angles are complementary.
And these are complementary, so that means you're dividing two things that are equal. And when you divide two things that are equal, you always get 1. Now, if you mess that up and you make it like 71 degrees, well, now you can't do it. So it's a very specific situation. Any questions on that?
Does that mean that the co stands for complementary?
Well, I can double check what it stands for. Actually, off the top of my head, I don't know. I don't think it does, but I'll double check once I put up the homework. Okay, so the homework, it's mostly in the book. That's the 1 through 14, 16, 18, 21 to 23. But I do want you to simplify sine 40 over cosine 50 and tangent 35 minus cotangent 55. So those last two problems are not in the